You hear people say, "We went to the moon in 1969, so why is it such a big deal to go back now, like it was a normal trip you could just book again?" That question sounds simple, but it hides how extreme Apollo really was, and how different the target is today. You didn't inherit a reusable, stable go-to-the-moon button. You inherited the memory of a one-time push that almost nobody would fund or accept today. First key point, Apollo was a sprint, not a lifestyle. In the late 1960s, NASA was getting around 4.4% of the entire US federal budget. That is more than $25 billion back then, which translates to well over $150 billion in today's money, pushed into a single, focused program. It was a Cold War movie, one country trying to prove to another that it could do something technically outrageous. It was not designed to be affordable forever, though democracy keeps spending that level of money for that long on one symbolic target. Once the flag was on the surface, the reason to keep burning that cash dropped fast. So when someone says, "We already did it, why not just do it again?" they are skipping that Apollo lived on crisis funding, not normal funding. So then you might think, fine, we don't need that much money anymore. Technology has improved, rockets are cheaper, so why not just pull the old designs out of the archive and redo them? That leads to the second problem. The hardware is gone, and most of the people are gone as well. The Saturn V is still the most powerful rocket ever flown to orbit. At liftoff, it produced roughly 35 million newtons of thrust, enough to send about 140,000 kilograms, around 310,000 pounds, into low Earth orbit. But no Saturn V exists in a flight-ready form. The factories that built its stages were shut down. The custom tools were scrapped. Many of the companies merged, changed focus, or disappeared completely. Even when you have the documents, a lot of vital know-how was never fully written down. It lived in the skill of welders, machinists, test engineers. They knew which welds were temperamental, which valves liked to stick in cold weather, which part of the test data you never trusted, unless you checked it twice. That kind of tribal knowledge fades when people retire or die, so rebuilding Apollo hardware today is not following the recipe. It is recreating an entire industrial ecosystem under modern rules with different suppliers and materials. That is basically a new program with old branding. But say you somehow clone the Saturn V exactly, you still hit the next reality. The moon was never easy, and it is not easier just because you did it once. To reach low Earth orbit from the surface, your spacecraft has to reach a speed of about 7.8 kilometers per second, roughly 28,000 kilometers per hour, around 17,500 miles per hour. If you include gravity and losses, the rocket engines have to deliver closer to 9.4 kilometers per second worth of push. Then to head for the moon, you need another boost of around 3.2 kilometers per second, about 7,200 miles per hour. After that, you still have to slow down for lunar orbit, slow down again to land, speed up to leave the surface, and control your fall back into Earth's atmosphere. Each of those burns has to be controlled very precisely. A small mistake, a difference of only a few hundred meters per second in speed, can mean the lander comes up short and crashes, goes long and skips, or misses the moon's gravity in the right way. When Apollo 11 landed, the lander had on the order of seconds of fuel left. If they had hesitated a little longer, they would have run out. That is how thin the safety margins were. So no, the moon is not right there in an easy way. It is one success stacked on top of another, with little room for error at each step. At this point, you might say, all right, send robots, prove the tech, then add humans later. But human missions are not just robot missions with seats bolted on. Human rating is brutal. A cargo rocket can accept a certain chance of failure, because the worst case is you lose hardware and money. The moment you add people, the acceptable risk drops sharply. You need emergency escape systems during launch, so the crew can be pulled away if the main rocket starts to fail. You need multiple backup systems for guidance, for communications, for power. You need life support that can keep oxygen, carbon dioxide, humidity and temperature in the right range for days or weeks, not just hours. You also need abort options at almost every phase. What if an engine dies during ascent, during the burn to the moon, while entering lunar orbit, or during descent? Each scenario needs a plan, hardware to support that plan, and training so the crew can actually execute it under stress. There's difference between a rocket that launches satellites and a rocket that launches people is not just a few extra checks. It is a different level of design, test, and verification for every major subsystem. That adds cost, time, and complexity everywhere. And even if you accept all that, there is a final twist. The goal itself is no longer the same. In Apollo, the mission definition was clear and limited. Land humans on the moon, walk, collect samples, come back alive. That was considered enough. Today, that would be seen as a short demonstration, not a full program. Now the expectation is, build up a long-term presence, test how to use local resources like water ice, prepare for Mars by learning how to live away from Earth for months, maybe years. People talk about habitats, power grids, rovers that can run for decades, even industry. So the target moved from do a handful of landings to build the early stages of a whole off-world infrastructure. That is much harder. You cannot just repeat Apollo and call it done, because the bar for success is higher. At the same time, NASA's slice of the budget is far smaller than in the Apollo era. Public patience is lower and safety expectations are higher. You're being asked to do more with less in a harsher environment. When you put all of this together, the old question we did it in the 60s, why not now, breaks down. Back then you had a temporary flood of money and urgency and a custom industrial machine that no longer exists, a one-shot objective and risk levels that would not be accepted today. Now the mission is to make moon access routine and sustainable, not dramatic and one time. That is a completely different challenge. And underneath all of that, there is something even more unforgiving. No matter how much money you spend or how good your engineers are, you still have to fight the same physics that Apollo did, the same gravity wells, the same fuel limits. The basic math of rockets did not get kinder just because a previous generation succeeded once. So the next step is to look straight at that and see why the rocket equation does not care about nostalgia or about your childhood memories of moon landings. You've seen that hardware and money all got harder, but there's a deeper problem underneath all of that. The physics did not get kinder just because humans walked on the moon once. The numbers are the same, the gravity is the same, the fuel requirements are the same, and they don't care that you have old black and white footage saying, we did it already. So start with the core of it. The rocket equation doesn't care about nostalgia. In simple terms, there's a relationship between how fast you want your spacecraft to end up going, how powerful your engines are, and how much of your rocket has to be propellant instead of useful stuff. That speed budget, the total delta V for a full moon mission, is around 10 to 11 kilometers per second. If you add up all the burns with some margin, that's 10,000 to 11,000 meters every second, tens of thousands of kilometers per hour. To do that with chemical rockets, which top out at a certain efficiency, your rocket becomes mostly fuel. That means for every kilogram of astronaut, life support and science gear, you're carrying many kilograms of propellant, easily tens of kilograms if you count all the stages. You can't cheat this. If you add more fuel, you made the rocket heavier, so you need more fuel to push that extra fuel. This is why moon rockets are stacked in stages. You throw away empty tanks and engines along the way so you're not dragging en masse. When you look at a launch tower and see a huge rocket, only a small fraction of that total mass is the crew vehicle and lander that actually go near the moon. Everything else is there to push that tiny useful part up to the required speed and then gets dumped. Now ask yourself this. If just meeting the raw speed requirement already forces you to build a flying fuel tank the size of a skyscraper, what happens when you start asking for more payload, more safety, more redundancy, without getting some magic new engine that is twice as efficient? That's where the gravity wells come in, Earth's and the Moon's. Earth's escape velocity is about 11.2 kilometers per second, roughly 25,000 miles per hour. The Moon's escape velocity is about 2.4 kilometers per second, around 5,400 miles per hour. Those numbers tell you how hard gravity is holding on to you. You don't always need the full escape speed for every maneuver, but it shows the scale of the problem. To reach the Moon and come back, you climb out of Earth's deep well, fall into the Moon's shallower well, then climb out of that and fall back toward Earth in a controlled way. The margins here are surprisingly thin. A lunar lander that's a few hundred kilograms overweight, say 300 to 400 kilograms, roughly 3 or 4 adult humans can push you past what your engine and fuel reserves can support. On Apollo 11, during the final descent, they ended up off the planned landing site and had to hover longer, while Neil Armstrong looked for a safer spot. That extra time burned extra fuel. They touched down with something like 15 to 20 seconds of usable fuel left. If you count your breathing while hearing alarms and staring at boulders, that is the real safety margin they had. When you design a new system today, you're expected to give crews more breathing room than half a minute from empty on another world, and that pushes you to carry more propellant or more efficient engines, both of which are hard. If the wells are that unforgiving, what does the actual motion down into the moon's gravity look like when you finally commit to landing? Lunar descent is basically a controlled fall into a vacuum. On Earth, during re-entry and landing, you have thick air to help you slow down, and you can use wings or parachutes. On Mars, even with thin air, you still get some braking from the atmosphere, plus heat shields and parachutes. On the Moon, there is no air at all, zero. That means from the moment you start dropping out of lunar orbit, your only way to slow down is to fire your engines and keep firing them in a tightly controlled way until your vertical speed goes to almost zero right above the surface. Come in too steep and your engine has to kill a lot of speed in a short distance. If anything glitches, you hit hard. Come in too shallow and you risk skimming over the surface or bouncing into an orbit that is not what you planned. The descent path is planned down to very small changes in speed and altitude, tens of meters, seconds of timing, and then that path has to be updated in real time as radar sees the actual terrain and the guidance computer reacts. You cannot joystick the whole thing from Earth. The round-trip signal delay is at about 2.5 seconds, too slow, so you need a system where the onboard computer and the crew handle the final part almost on their own, with very little external help, and any bug in that software or misread in the sensors can end the mission in a crater. And even if you solve the descent math, the surface itself fights you. Lunar dust and regolith are not friendly. The particles are small, often below 50 micrometers in size, less than 1/20th of a millimeter, and they are sharp. They were created by billions of years of micrometeorite impacts in vacuum, not by wind and water smoothing them. So you get jagged grains that cling electrostatically to suits and hardware. When a lander engine fires near the surface, the exhaust plume hits that loose regolith and throws it out at high speeds, hundreds of meters per second, similar to a very fast car in terms of speed, but now it's abrasive dust instead of air. That cloud can erode landing legs, blast rocks into the air, sandblast other nearby equipment, and coat windows, cameras, and solar panels. It can also dig out the soil under the lander unevenly, which risks tilting the vehicle or stressing the landing structure in ways you did not fully predict. During Apollo, mission times on the surface were short, and there were no other landers parked nearby, so the environment was simpler. For future missions, where you might have multiple landers in the same region and longer stays, you have to think very carefully about how to control plume effects, how to design landing pads, and how to keep dust out of habitats and machinery. If you don't, the environment slowly eats your systems. Now add one more layer. What happens when you stop treating the moon as a short visit and start talking about bases, cargo deliveries, and real logistics chains? Scaling up for bases makes the physics harsher, not kinder. A small lander carrying 2 astronauts and a few hundred kilograms of gear already stretches your margins. A cargo lander designed to deliver 10 to 20 tons of equipment, 10,000 to 20,000 kilograms, around 22,000 to 44,000 pounds, puts you in a different regime. Every extra kilogram you want to place gently on the lunar surface forces you to add more fuel to the lander itself. That heavier lander then needs a bigger booster to send it from Earth, and that booster needs more stages and more fuel. The whole stack inflates. The rocket equation punishes you for heavy payloads in a non-linear way. Doubling your payload does not just double your fuel, it can more than double it once you include structural mass and staging limits. That means that building a base, which needs repeated heavy cargo deliveries, is physically and economically much nastier than doing a few light crewed landings. You are now designing a system that has to be efficient in ways Apollo never was, because Apollo could afford to be wasteful for a few missions. A sustainable program cannot. So when you hear people say, "We already know the way, it's just budgets," the full answer is sharper. Yes, budgets are a huge part, but even if you froze all that in your favour, you would still be fighting the same gravity wells, the same descent challenges, the same dust, and a rocket math that heavily resists big routine payloads. This is the baseline difficulty before you even talk about industrial supply chains or safety regulations. And if the raw physics is already this tight, with seconds of fuel left, rockets mostly filled with propellant, and thin margins for landing and takeoff, what happens when you look at the massive machine that had to exist on Earth to build all this in the first place, and realise that entire machine was shut down on purpose? You've seen how the physics is already pushing everything to the limit. Now here's the next uncomfortable piece. The giant machine on Earth that once made moon rockets was basically turned off and dismantled, and you're not getting it back by printing a few blueprints off a server. Start with the big one. The Saturn V was not just a rocket, it was a one-off custom industrial project the size of a national emergency. It stood about 110 meters tall, roughly like a 36-story building, and fully fueled it had a mass of around 2,900 tons, about 6.4 million pounds. But that's just the hardware you see in photos. Behind it was an ecosystem of thousands of companies and hundreds of thousands of people spread across the United States, all tuned to one goal: beat the Soviet Union to the moon fast. Machine shops, test stands, fuel tank factories, engine plants, instrument labs, all synchronized around Apollo schedules. Once Apollo 11 landed and a few more missions followed, the need dropped. The race was declared won. That huge industrial network was no longer protected. Budgets shrank, contracts ended, people shifted to other projects or other industries. The system that could build a Saturn V on demand was not mothballed neatly in a warehouse. It was allowed to collapse. So when someone says, "We did Saturn V in the 60s, let's just do that again," they are talking about a machine that no longer exists, not a product sitting on a shelf. So you might push back and say, "Fine, the old factories are gone, but we have the drawings, we have the data, just rebuild it with modern tools." That sounds clean, but it runs into the next problem. Even the hidden details of Apollo's hardware have disappeared. You cannot simply rebuild a Saturn V from blueprints the way you'd rebuild a Lego set from instruction. The rocket depended on specific metal alloys, specific welding techniques, specific heat treatments, and lots of small but critical parts like valves, seals, fasteners, that came from vendors who are long gone. Even when the paperwork survives, it often assumes knowledge that lived in people's heads, not in the documents. A note might say weld per standard X, and everyone at the time knew that really meant use this particular sequence in this temperature range on this machine or it will crack. That context lived in the experience of the people on the production line. Those people retired in the 1980s and 1990s. So to rebuild Saturn V today, you would have to requalify materials, redevelop weld procedures, retest entire engines, and reopen long chains of suppliers. That is basically the cost of designing a new rocket, with extra constraints, not the cost of copy-paste. And even if you could resurrect that older design exactly, there's a third wall. A lot of what flew in Apollo would be considered too risky under modern safety and quality standards. Back then, people accepted levels of danger that are not acceptable now. Some materials used in Apollo hardware, like certain insulations and sealants, contain things we now try to avoid, like asbestos or very toxic chemicals. Wiring practices, fault tolerance in electronics, and software validation were all far less strict than today's human rating rules demand. If you tried to certify an Apollo-style spacecraft today for a modern, crewed mission, you would run straight into updated regulations for everything from fire safety in the cabin, to how many independent computers you need, to how your software must be tested. To pass those rules, you would have to redesign large chunks of the system, change the materials, change the electronics, add more redundancy, add better fault isolation. At that point, you're no longer flying Apollo again, you're flying a different vehicle that just looks similar at a distance. Holding up Apollo as a template ignores that we have, on purpose, raised the bar for what we consider acceptable risk. So maybe you think, forget Saturn V, we have a new generation of rockets now, right? Falcon 9, Falcon Heavy, Ariane 6, Long March, New Glenn, all of these. Can't we just point one of those at the moon and get on with it? The issue here is that today's main workhorse rockets were designed to solve a different problem, not to replicate Apollo. Their main job is to put satellites into low Earth orbit, maybe around 400 kilometers up, or send them to geostationary transfer orbit, roughly 36,000 kilometers out. Those orbits support GPS, weather satellites, communications, Earth observation. That's where the money is. So their design is optimized around that market in terms of payload mass, fairing coys to Mars reusability, launch cadence, and cost per kilogram. The Moon, at roughly 384,400 kilometers away, almost 1,000 times farther than low Earth orbit, needs a different architecture. For a serious lunar program, you need heavy lift to put big chunks of mass into orbit, plus transfer stages, plus landers. You might refuel in orbit or use multiple launches to assemble a mission. You cannot just take a rocket tuned for throwing satellites to geostationary orbit and expect it to serve as a plug-and-play moon launcher without major modifications or extra hardware. That means more design work, more testing, more points of failure. This leads into what is happening now with things like Artemis and the Space Launch System. The current plan for US crewed lunar missions is built around a new heavy-lift rocket that can loft on the order of 70 to 130 tons into low Earth orbit, roughly 154,000 to 286,000 pounds, similar territory to Saturn V. It reuses some shuttle heritage engines and boosters, but wraps them in new structures, new tanks, and new avionics. Parallel to that, there's Orion, a new crew capsule and various lander concepts, some fully commercial, some not. What that really means is, you're not bringing back Apollo capability, you're building a new industrial base from scratch in a different era with a different technology, and under constant pressure to be cheaper and safer at the same time. You're trying to spin up a machine involving governments, legacy contractors, and new commercial players, while the audience outside asks why it is taking so long when we already did this. That gap between expectation and reality is a huge part of why the whole thing feels stuck. And remember, all of this industrial difficulty sits on top of the raw physics and fuel problems you heard earlier. You still have to fight gravity, you still have to manage razor-thin margins on landing and ascent, you still have to deal with dust and vacuum and harsh temperature swings. But now, on top of that, every bolt and cable and line of code has to survive a complex supply chain, tight safety rules, funding fights, and changing priorities. So if the Earth side machine that once pushed humans to the moon has been torn down and rebuilt in a completely different shape and the new machine is trying to do more, with less margin for error, what happens when you add one more factor? The fact that the money and the public attention span behave like their own kind of gravity well, constantly pulling the whole project back down. You might think that once humans reached the moon, money support would lock in and stay strong, but the reality went the opposite way. The moment the flag went up, the budget started falling off a cliff. Right after Apollo 11 in 1969, public interest dropped fast. The first landing was huge, but by Apollo 12, TV networks were already cutting away from live coverage. By Apollo 13, people were barely paying attention until the oxygen tank exploded and it turned into a survival story. And once Apollo 17 flew in 1972, that was it. No more moon landings. At the peak of Apollo, NASA was sitting at around 4.4% of the US federal budget. In the years after, that fell to well under 1%, and it has stayed down there. So you go from throw everything at the moon to you're just one line item among many. Trying to run a long-term lunar program after that is like trying to keep running with most of your fuel cut off. The paradox is, the more normal the moon started to feel to the public, the less willing they were to pay for it. So if the excitement collapsed that fast after the first steps, what happens when you ask for money again, not for a one-time stunt, but for a slow grinding build-up. That's where the competition kicks in. Space is not alone in the queue. Every national budget has heavy hitters: healthcare, defense, pensions, education, climate projects, social programs. All of them have strong lobbies and direct, visible impact on voters' lives. Against that, a modern lunar program is asking for tens of billions of dollars spread over 10 to 20 years. One big flagship mission can easily be in the $10 to $20 billion range by the time you count development, hardware, launches and operations. To you, the idea of building a permanent presence off Earth sounds like a clear win. To a finance minister, it's one very expensive project competing with hospitals, fighter jets and flood defences. That leads straight into another problem. Start-stop quietly destroys momentum. Space agencies do not just pick a plan and follow it in a clean straight line. You see big shifts. Constellation was announced, then reworked, then cancelled. The Space Launch System and Orion came out of that shuffle. Then Artemis was layered on top as the new Go Back to the Moon brand. Each change means renamed milestones, altered goals, and often hardware that gets partly built and then abandoned. Every time that happens, you waste more than metal and money. You waste engineering knowledge, software, test data, and human experience. Teams get broken up, contractors lose staff, younger engineers see that years of work can just vanish when a new administration changes course. It's like being told to build a tall tower, and every few floors someone shows up and says, "New design, tear down this section, start over with different materials." You can do that once or twice, but after a while people stop believing that the current plan will survive. And if the people inside the program don't fully trust that the target will hold still, how much real progress can they make before the next reset hits? Then there's the shift in how much risk society is willing to accept after disasters. The Challenger shuttle was lost in 1986, Columbia in 2003, 14 astronauts total. Those events hit live on television and in the internet era, with endless replays and investigations. They rewired how NASA sees risk and how the public react to it. During Apollo, everyone knew it was dangerous, but there was a different baseline expectation. The Cold War mindset, the urgency to beat the other side, made high risk feel tolerable, at least for a while. Now, a single fatal accident could freeze human spaceflight for years, especially if it happens on the way to the moon, where it looks like we pushed too far. The moon itself has not become safer. The vacuum is still vacuum. The dust is still abrasive. The landings are still hard. So a cautious lunar program today means more redundancy, more testing, more independent reviews, and more backups for backups. All of that takes money and time. The public demand that you reduce risk as close to zero as possible, but physics guarantees you can never hit zero. So how do you convince everyone to accept that real, non-trivial danger is still there, while also demanding that the program moves faster and costs less? Finally, there's the uncomfortable fact that the return on investment from the moon is subtle and slow, at least on paper. If you build a bridge or a hospital, people see it, drive across it, use it within a few years. If you cut taxes, people feel it in their paychecks. That's easy to sell. Lunar exploration pays off in ways that are harder to point at in a budget hearing. You get technology spin-offs scattered across industries, new materials, new software, better communications, medical advances from life support research. You get inspiration, kids going into science and engineering because they saw a new moon mission. You get a small but real step toward long-term species survival by learning how to live off Earth. But all of that is diffuse. It's spread out over decades across millions of people, and nobody can say this one gadget exists only because of this one moon mission, in a clean, simple way that wins arguments in a crowded budget meeting. So when money gets tight or when some other crisis hits, space looks like something you can trim because nothing collapses the next day if you do. For you, as someone watching this, the idea of humans building a stable presence beyond Earth is obviously worth it. For a committee writing next year's budget, it can look like a luxury. So even if you somehow win that argument and keep the funding stable, you still have one more layer of difficulty to deal with. The hardware is built by human bodies, and those same fragile bodies have to ride the rockets, step onto the surface, and live in an environment that evolution never prepared them for. When you add biology to this already tight system, the moon stops being just an engineering target and turns into a direct attack on the limits of the human organism itself. Here's the part that's easy to ignore. Your body is not built for deep space, and the moon does not care how tough you think you are. Start with radiation, because that hits you before you even get close to the surface. Low Earth orbit, where the ISS flies at around 400 kilometers, still sits mostly inside Earth's magnetic shield, the magnetosphere. That field bends a lot of charged particles away, so astronauts on the ISS see dose rates on the order of about 0.3 to 0.5 millisieverts per day. That's already higher than on the ground, but it's manageable for limited time. Once you leave that shield and head for the moon, you cross the Van Allen belts and then you're in deep space, with almost no protection. Now you're dealing with galactic cosmic rays and bursts from the sun called solar particle events. Dose rates jump up to around 1 to 2 millisieverts per day, sometimes higher during bad solar weather. Over a mission that lasts a few weeks to a month, the total dose can reach the level of several chest CT scans or more. That kind of radiation raises lifetime cancer risk, can damage bone marrow, and can hit the central nervous system. To cut the dose you need shielding, but shielding means mass, and mass means more fuel, which runs straight into the rocket problems we already talked about. You end up with compromises. Some areas of the spacecraft are more shielded storm shelters, and astronauts move there during solar events. The rest of the time, they accept a dose that is above all normal Earth conditions. So even before you land, you're trading long-term health for mission goals, and that's for relatively short trips. Stretch that to multi-month lunar operations, and the numbers start to look very serious. And that is just the radiation side. So now ask, what happens to your body when gravity basically turns off for days at a time, then comes back in a weaker version your muscles and bones have never experienced? In microgravity, your skeleton and muscles start to detrain fast. On the ISS, we see bone density losses of roughly 1 to 2% per month if countermeasures aren't aggressive, and muscle mass falls quickly as well, especially in the legs and back. The cardiovascular system adapts too. Fluids shift toward the upper body, the heart doesn't have to work as hard to pump blood upward, and it starts to remodel. For a trip to the moon, you get several days in microgravity going out, some days on the surface and several days coming back. Even a 10-day or 2-week mission stresses a body that has lived at 1G its entire life. Astronauts use exercise machines in orbit, treadmills with harnesses, resistance devices, to slow this down, but you never fully cancel the effect. Then you ask those same people to do precision work in a heavy suit under time pressure after their balance system, muscles and heart have been retuned to weightlessness. Reaction times can change, fine motor control can be off, orthostatic intolerance can hit when they stand in gravity again. That's not a great setup for operating complex systems in an environment where a simple mistake can be fatal. And microgravity isn't even the final state on the moon. So the next question is, what does it mean to live and work at 1/6 G, a gravity-less level no human body evolved for? On the lunar surface, gravity is about 1/6 of Earth's. So if you weigh 90 kilograms on Earth, around 200 pounds, you weigh only about 15 kilograms, 33 pounds on the moon. That sounds fun, but biomechanics are not that simple. You're too light for your normal walking pattern to work properly, but still heavy enough that a fall can hurt. Apollo astronauts reported a sort of loping, hopping gait instead of the normal walking, and they fell more than once. Add the suit, which can be over 100 kilograms in mass, about 220 pounds plus life support on top of an 80 kilograms, 176 pounds astronaut. The total mass you have to control is large, even if the weight is lower in 1/6 G. When that stack starts to tip, you can't just casually correct it, inertia is still there. Your centre of mass is higher, your range of motion is limited by the suit, and the surface is uneven and dusty. The result is a walking system that feels unfamiliar and unstable exactly when you need reliability. Short missions can get away with a bit of clumsiness, but if you plan to send crews out for long EVATs, day after day in that regime, the chance of injury rises. A broken ankle, a torn ligament, or a concussion on the moon is not the same as a sports injury on Earth, because medical care is extremely limited and evacuation takes days. So far, we're talking about stays measured in days or weeks, but the whole point of going back is to stay longer, which raises a harder question. What happens to human biology in 1/6 G over months or years, when almost no data exists? We basically have 2 gravity data points today, Earth at 1G, and orbital platforms like the ISS at something very close to 0G. Everything in between is mostly unknown for long durations. We do not really know how partial gravity, like 1/6 G, affects long-term bone health, muscle maintenance, heart function, brain structure, or immune system. Does 1/6 G stop bone loss or just slow it a bit? Does it fix the fluid shifts or leave you with a constant low-level problem? What happens if a child is conceived and grows up in that environment? We have almost no human data there. If you build a lunar base and put crews there for 6 months or a year at a time, you're turning them into test cases in a gravity regime human evolution never saw. You can model, you can run animal studies, you can simulate bits of it with centrifuges, but you will not truly know the full medical picture until you do it with real people, over long spans of time. That means accepting uncertainty is not just about mission performance, but about long-term health, fertility, aging, and mental function. It is a medical experiment on top of an engineering experiment, and all of this assumes that the machines keeping you alive keep doing their job, which leads to the last brutal layer. Life support on the moon is a closed loop that has almost no forgiveness. On Earth, you treat air, water, and food as background. On the moon, every kilogram of oxygen, water, and food you don't produce locally has to be launched from Earth. With launch costs in the thousands of dollars per kilogram to low Earth orbit, and more to push it onward, that adds up fast. So you are forced into regenerative systems. You recycle carbon dioxide into oxygen with chemical scrubbers or more advanced loops. You reclaim water from humidity in the air, from sweat and from urine. You carefully manage waste. The aim is to close the loop as much as possible, so you aren't constantly shipping basic supplies. But closed loops are unforgiving. A small leak in the habitat structure, even a fraction of a percent of atmosphere per day, slowly drains your air. A subtle failure in a water recycling unit can send contaminants back into the system and make people sick. A stuck valve in a CO2 scrubber can let levels creep up without being obvious at first. On Earth, you call a repair crew or order a replacement. On the Moon, you are 384,400 kilometers away, about 239,000 miles, with resupply windows measured in days and hardware replacement months out. You have to carry spares, test procedures, and crews trained to repair almost everything on site in a cramped environment with limited tools. That means if life support isn't working close to perfectly all the time, you are living with a slow countdown in the background. Your margin is not big. There is no quick escape route, no safe fallback environment. You are relying on a bubble of technology, a few centimeters of metal and composites, and software that must run non-stop without major mistakes. And that's before you step outside that bubble into a suit, where your entire life support train shrinks down to systems strapped directly to your body. So if just existing near the moon pushes your biology, your radiation limits, and your life support systems right to the edge, what does it look like when you actually go out onto the surface where the temperature swings are extreme and the dust cuts into everything and the environment is constantly trying to punch holes in your protection? You might think that once the lander touches down, the hard part is over, but the surface is its own kind of hostile, and it starts attacking your gear and your body the second you arrive. First problem, the temperature swings are brutal. On the moon, in direct sunlight, the surface can heat up to around plus 120 degrees Celsius, about 250 degrees Fahrenheit. In the long lunar night, it can drop to around minus 170 degrees Celsius, about minus 274 degrees Fahrenheit. That's a swing of almost 290 degrees Celsius across a lunar day. There's no air to smooth that out, no wind to carry heat away or bring warmth in. It's just raw radiation from the sun, or empty cold facing deep space. Your suit, your lander, your tools, your cables all have to survive without cracking, warping or losing pressure. Metals expand and contract, plastics stiffen, seals harden, electronics see huge thermal cycles. If your design isn't rock solid, tiny cracks become leaks, solder joints fatigue, and suddenly your reliable system isn't so reliable anymore. And this doesn't happen once, it repeats every lunar day-night cycle, over and over, for as long as you want to keep anything alive up there. Even if you solve the thermal control, the surface hits you with the next problem, the dust. Apollo crews talked about this a lot. Their suits came back into the lander coated in fine grey regolith that stuck to everything. That dust is not like beach sand. The grains are tiny, many smaller than 50 micrometers, but more importantly, they're jagged. There's no atmosphere and no water on the moon to round off edges, so you get sharp angular particles, basically ultra-fine glassy grit. It gets into suit joints and starts acting like sandpaper. It abrades seals and bearings, it scratches visors. When it gets into the cabin, people breathe it in, and it can irritate lungs and eyes. Because the surface and the equipment can pick up electric charge, that dust also sticks electrostatically, clinging to fabrics and surfaces you thought were clean. Over longer missions, that turns into a major maintenance headache. You can't just say, we'll sweep it up. You need better seals on airlocks, filter systems that can handle constant contamination, and maybe designs where suits stay attached outside the habitat so dust never comes in with the person. If you don't take this seriously, your nice, clean, expensive base slowly turns into a dusty, abrasive environment that chews through hardware and affects crew health. And that's only the material sitting on the ground. You also have material constantly arriving from space. Because the moon has no atmosphere, micrometeorites never burn up. Even very small particles, a few millimeters or less, slam into the surface at tens of kilometers per second, much faster than a rifle bullet. Each impact delivers a lot of energy in a tiny spot. Over months and years, that bombardment erodes exposed surfaces, chips away at structures, and can puncture thin layers. Habitat walls, radiators, external tanks, and suits are all in the line of fire all the time. To handle that, you don't just put up a thin metal wall and hope. You start using layered protection, things like Whipple shields, where a thin outer layer breaks up the particle before it hits the main wall, or you pile regolith over parts of the habitat to act as a natural shield. Both approaches add mass and complexity. Every extra centimetre of protective material costs you fuel to deliver or effort to move. For a short mission, you can accept more risk, but for a base that's supposed to last years, you're adding shielding mass and design constraints everywhere. That's more weight in your rockets, more structure to carry, more things to build with robots or crews on the surface. So what keeps a human alive in the middle of all this? The radiation, the temperature swings, the dust and the micrometeorites for hours at a time outside the habitat. It's the suit. And the suit is basically a tiny spacecraft wrapped around one person. A next-generation lunar EVA suit has to do a lot of jobs at once. It has to hold a stable internal pressure, typically on the order of 30 to 50 kilopascals, so your blood doesn't boil and your lungs can work. It has to provide oxygen and remove carbon dioxide. It has to control temperature, pulling heat away from your body when you work hard and preventing you from freezing in shadow. It needs communications gear, so you can talk to teammates and to the base. It needs a visor and layers that block ultraviolet and some radiation. And on top of that, it has to let you move, bend, twist, grip tools, and climb. All of that hardware, plus batteries and life support units, comes to something like 80 to 90 kilograms of mass, around 175 to 200 pounds. In lunar gravity, that weighs less, but the inertia is still there. When you try to move, you're pushing around that full mass. If the suit is too stiff, every step costs a lot of energy, and fatigue builds up fast. Hands can get injured from fighting glove pressure, shoulders and hips get sore from struggling against stiff joints. And this isn't a one-off photo op, you want suits that can support 8-hour spacewalks, again and again, with minimal maintenance in a place with limited tools and spare parts. That is a tougher design challenge than most cars, and if it fails, the breakdown is instantly life-threatening. Now, scale this up over time. Apollo astronauts spent hours to a few days on the surface per mission. They were basically on an extreme camping trip in short bursts. Future missions talk about weeks on the surface, followed by months, and eventually continuous presence with rotating crews. That changes how you think about failure. A slow leak in a suit system or habitat that would be annoying but manageable over 3 days becomes a serious threat over 90 days. Filters that clog a little faster than planned, seals that wear just a bit quicker, dust that builds up in one corner of the airlock, all of that compounds. If you're staying for 3 days, you can afford to say, "We'll fix it when we get home," or "We'll just deal with the discomfort." On a 90-day mission, those small issues are exactly what snowball into big problems. Extra risk on every EVA, more downtime, more crew stress. You're moving from a short visit to trying to live in a place where everything outside your walls is either too hot, too cold, too sharp, or moving too fast. The moon does not give you an easy mode just because you planted a flag there once. And remember, all of this is just about not dying while you stand on one small patch of ground. You still have to navigate there, talk to Earth, and operate with a built-in delay and limited bandwidth. Once you stretch your operations across the near side, the far side, polar regions, and orbit, the next layer of difficulty hits. The fact that space around the moon is a communications and navigation maze, and you can't just drive your lander like a remote-controlled drone from your living room. You probably think light is fast, so talking to the moon must be instant. But even at the speed of light, the distance hits you in the face as soon as you try to actually control something there. Radio waves move at about 300,000 kilometers per second, around 186,000 miles per second. The moon is roughly 384,400 kilometers away, about 239,000 miles. That means a signal from Earth takes a bit more than a second to get there, and the reply takes a bit more than a second to come back. Round trip, you're sitting on a roughly 2.5 seconds of delay. That doesn't sound like much when you just say the number, but try to control anything in real time with that lag and it breaks your brain. You press a button, you wait, the thing reacts, you see the reaction, you adjust, you wait again. You cannot joystick a lander the way you fly a drone. By the time you see that it's drifting, it has already drifted more. So you pre-program the landing sequence, you let the onboard guidance do most of the work, and humans step in only at specific points, with limited authority, and always with that delay baked in. The moon is close in a cosmic sense, but from a control standpoint, it's already outside the real-time zone your instincts expect. Then there's a more brutal communication problem hiding behind that. Half the moon literally never faces you. The moon is tidally locked. It always shows the same side to Earth. That means the far side, the back, never has a clear line of sight to our planet. Without relay satellites in the right places, anything you land there is radio dead to Earth. No live telemetry, no live voice calls, nothing. To fix that, you need infrastructure, spacecraft in lunar orbit that act as repeaters, or satellites parked in special orbits, like halo orbits around the Earth and Moon L2 point, where they can see both the far side and Earth. Every relay satellite is one more launch, one more spacecraft to design, power, and then maintain, one more object that can fail at the worst possible time. So the moment you say, let's explore the far side, let's put radio telescopes there, let's put a base near those polar craters, you've committed to building a little comms network around the moon first, before anything else really works. Even when you do have links, just staying in the right place above the moon is not as clean as you might think. The moon's gravity field is not smooth, it's lumpy. There are mass concentrations, called mascons, buried under the surface from ancient giant impacts, and those extra masses tug on orbiting spacecraft in uneven ways. Over time, they nudge orbits, changing altitude and ground track by tens of meters, then hundreds, then more, if you don't correct them. For high orbits, that's annoying. For low lunar orbit, the kind you want for detailed mapping, or as a staging orbit before descent, it can be mission critical. Your descent path assumes you start from a certain point with a certain speed. If the orbit has shifted, those assumptions go wrong. A few tens of meters off in the wrong direction, at the wrong time, can be the difference between descending into a safe flat plane and pointing yourself right at a slope or a crater wall. So you need very accurate gravity maps, constant tracking, and regular orbit adjustments. You're not just flying through empty space, you're surfing a slightly warped gravity field that keeps trying to kick you off. On top of all that, every bit of data that goes back and forth has to share limited ground infrastructure on Earth. Deep space missions don't talk through random dish antennas, they use the Deep Space Network and similar big radio sites with dishes up to 70 meters across, backed by serious electronics. Those same antennas are already talking to Mars orbiters and rovers, probes heading to Jupiter and beyond, SUR observatories and more. The bandwidth and tracking time are finite. A human lunar mission suddenly demands a lot. High data rates for video, telemetry, voice, plus priority scheduling, because lives are on the line. That means you either build more antennas, upgrade existing sites, or you steal time and bandwidth from robotic missions. There is no magic extra channel. Everything is a trade, and deep space capacity becomes a shared bottleneck the moment you start running crewed flights beyond low Earth orbit on a regular basis. All of this leads to a simple but uncomfortable conclusion. Autonomy around the moon is not a luxury, it's compulsory. Because of the light speed lag and the limited bandwidth, landers, rovers, orbiters, and eventually habitats and power systems all need to make a lot of decisions locally. Automatic hazard detection on landing, automatic rerouting of power when something fails, fault detection and isolation in life support, local navigation for rovers that can't wait seconds for a turn left command. All of that has to run on board. You're basically putting AI-like control systems into environments where mistakes can kill people. That means more complex avionics, more software, more sensors, and deep verification work. Every extra line of code is one more chance for a bug that only shows up in some rare timing condition, when a sensor glitches at the same time a cosmic ray flips a bit. You have to test these systems in sims, in hardware-in-the-loop setups, over and over, because you can't patch your way out of a bad landing as easily as you patch a smartphone app. So when you zoom out, the navigation and communication layer is not just point antennas and go. It's a whole extra stack of problems, delay you can't remove, dead zones you must cover with infrastructure, a warped gravity field that won't leave your orbits alone, shared networks that can't perfectly serve everyone, and autonomous systems that must take over critical operations without you looking over their shoulder in real time. It's one more reminder that the moon is already acting like a separate world, with its own local system you need to build and manage, not just a distant hill you shoot a rocket at. And yet, all of these challenges still sit on top of an even more basic limit, the engines and fuels you're using to move everything around. You're pushing up against what chemical propulsion can realistically do. You're juggling cryogenic propellants that want to boil away, and you're stuck between hypergolic fuels that are reliable but toxic, and green propellants that aren't magic either. If the physics and the distance and the comms are this brutal, what happens when you stare directly at the heart of it? The propellant tanks, the engines, and the fact that the chemistry itself is close to maxed out. You'd think the fuel problem would be the easy part by now, because we've been flying rockets for decades. But the ugly truth is, with chemical rockets, you're already close to the ceiling and there isn't some magic new fuel around the corner that doubles your performance. The classic propellant pairs, like RP1 kerosene with liquid oxygen, or liquid hydrogen with liquid oxygen, are already working near the thermodynamic limit of what chemical bonds can give you. A very good hydrogen-oxygen engine in vacuum reaches a specific impulse around the mid-400 seconds range. That's a measure of how efficiently it turns propellant into thrust. To get something like 800 seconds, you're not tweaking chemistry, you're jumping to totally different tech, like nuclear thermal or something even more exotic with its own risks. So your moon mission profile is boxed in by basic chemistry. You need around 10 to 11 kilometers per second total speed change over the full mission, but the engine efficiency is capped. That means the only levers you really have are the staging, mass fractions, and mission design tricks, not a miracle propellant that makes the problem go away. So if hydrogen oxygen is as good as it gets in chemical form, why not just use that everywhere, top to bottom, and enjoy the efficiency? What's the catch there? The catch is that hydrogen is a cryogenic nightmare. Liquid hydrogen only stays liquid at around 20 Kelvin, which is about minus 253 degrees Celsius, or minus 423 degrees Fahrenheit. Keeping something that cold for several days or weeks, inside a tank that's going through sun, shade, and all the vibrations of launch and spaceflight is brutal. You need thick insulation, complex tank designs, maybe active cooling systems. If you don't do that, the hydrogen slowly boils off, you lose propellant, and you have to start the mission with bigger tanks just to cover the losses. Every extra kilogram of insulation and equipment is a kilogram you don't get to spend on payload, science gear, or safety systems. It's a constant trade, performance versus practicality, and there is no clean win. So you might say, fine, if cryogenics are that painful, go with propellants that are easier to store, even if they're not quite as efficient. How bad can that be? This is where hypergolics and so-called green propellants come into the picture, and you learn there's no free option here either. Apollo's lunar module used hypergolic propellants, liquids that ignite the instant they touch each other, which makes them very reliable and simple from an ignition standpoint. No spark systems, no complicated start sequence, but those chemicals are extremely toxic and corrosive. Handling them on Earth needs serious safety gear and procedures, and you really don't want leaks near a habitat or crew. Modern programs are testing green propellants that are easier to handle and less toxic, but they often give you lower performance, or they introduce new engineering challenges, like different freezing and boiling points, or compatibility issues with materials. Right now, there is no magic propellant that is high performance, non-toxic, and easy to store for months in space all at once. So if all your propellant options are compromises, the next thought is, why carry it all from Earth? Why not make some of it on the moon and cut the problem in half? There's a real possibility there, but it's not as straightforward as people hope. The lunar poles likely hold water ice in permanently shadowed craters, where temperatures can plunge below minus 200 degrees Celsius, around minus 328 degrees Fahrenheit. In theory, you could mine that ice, melt it, split it into hydrogen and oxygen with electricity, and then liquefy and store those gases as rocket propellant. In practice, you're running a mining operation and a chemical plant in constant darkness, in vacuum, at extreme cold. You need robots or crews to dig, processing hardware that won't clog with dust or freeze solid, power systems that can run continuously, and storage tanks that keep your new propellant from boiling away. That isn't a gas station on the moon. It's a full refinery and industrial site built in one of the harshest environments you could pick. And if in-situ resources are that difficult, you might wonder, why not jump to something more advanced and skip the chemical box entirely? If nuclear thermal rockets can give you roughly twice the efficiency, why aren't we flying them already? Technically, nuclear thermal propulsion is very attractive. You heat a propellant like hydrogen with a reactor instead of burning it with oxygen, and you can push the effective efficiency, that specific impulse, to maybe double what chemical rockets can manage. That means smaller propellant loads for the same delta V, or more payload for the same rocket size. On the surface, nuclear reactors can also give you steady power through the 14-day lunar night, when solar panels are useless. But the moment you put nuclear and rocket in the same sentence, you run into public fear and resistance. People worry about launch accidents, about fallout, about space reactors being weaponized. Regulations become strict, approval takes years, and some countries or partners might not sign on at all. So the tech has promise, but its deployment is slowed down by arguments and concerns that have nothing to do with the physics or the engineering. So you end up with a tight box, chemical rockets that are near their natural limit, cryogenic fuels that are powerful but hard to store, storable fuels that are convenient but toxic or weaker, in-situ production that is possible but extremely hard to set up, and nuclear options that are technically strong but constrained. The propulsion problem is not just add better fuel, it's choose which kind of pain you want to live with, and then design your entire moon architecture around that choice. And even when you lock that in, you still haven't solved one of the nastiest constraints of all. The fact that on the moon, half the time there is no sunlight, temperatures plunge, and your systems have to survive a 14 Earth day night without freezing or dying. If the fuel and engines already push you to your limits, what does it take to keep a base powered and warm when the sun vanishes for 2 weeks straight? You've seen how hard it is just to land and move around, but there's a quieter problem that never goes away: keeping power and heat under control on a world where day and night last for weeks, not hours. The basic timing is already against you. One lunar day from one noon to the next is about 29.5 Earth days. Around the equator, that splits into roughly 14 Earth days of sunlight and 14 days of darkness in a row. During the day, solar panels work fine. Then the sun sets, and for 2 weeks straight, solar power drops to zero. If your habitat needs a steady 10 kilowatts just to keep lights on, air moving, life support running, and some basic systems operating, those 14 dark days are a huge problem. Do the rough numbers. 14 days is 336 hours. At 10 kilowatts continuous, that's about 3,360 kilowatt hours of stored energy just to bridge the night. And that's before you add safety margin, inefficiencies, heaters for equipment, and extra loads for emergencies. Once you pad it, you're easily talking in the range of 10,000 plus kilowatt hours. If your batteries store around 200 watt hours per kilogram, a decent modern figure, then 10,000 kilowatt hours is 10 million watt hours, which means about 50,000 kilograms of batteries, over 110,000 pounds. Even 3,360 kilowatt hours is around 17,000 kilograms. Shipping that much battery mass from Earth, plus the structure to mount and protect it, is not realistic for a small outpost. So you are forced to look for other tricks, and you start designing your whole base around that 14-day blackout. The obvious answer is, don't go to the equator, go to the poles. And that does help, but it doesn't magically solve everything. Some ridges and crater rims near the lunar poles get near continuous sunlight over the lunar year, with only short dips into shadow. That makes solar panels much more attractive there. But the water ice you care about, the stuff in permanently shadowed regions, sits down inside deep, cold craters nearby, where sunlight basically never reaches and temperatures can stay below about minus 200 degrees Celsius, around minus 328 degrees Fahrenheit. So you end up with a spread out system. Solar arrays sit up on high ground, where they can see the sun most of the time. Habitats might be partly buried in regolith for shielding. Mining gear and processing units for ice sit down in the dark, cold craters. You now need power lines or beamed power systems to move energy from the sunny ridges to the dark work sites. Every meter of cable or every extra power beaming unit is more mass to launch, more hardware to install, and more points that can fail, get hit by micrometeorites, or be damaged by dust. You've gone from place panels next to base to build a whole local power grid in a hostile environment. Then there's the flip side of power, what you do with waste heat. On Earth, you can dump heat into the air or water through convection. Fans and radiators move warm air away and pull in cooler air. On the Moon, there's no air. If you want to get rid of excess heat from electronics, life support, or reactors, you can only radiate it away as infrared light. That means you need radiators, big flat surfaces with fluid loops or heat pipes, pointed at the cold of space. Those radiators have to be exposed, which means they sit in the firing line for dust kicked up by landers and rovers, and for micrometeorite hits. Over time, dust sticking to the surfaces reduces their ability to radiate heat. Tiny impacts can puncture or degrade them. If your radiators underperform, your systems start to overheat, and you have to throttle back or shut down equipment just to stay within safe temperatures. It's like trying to cool a powerful computer using only a passive heatsink in a place where that heatsink slowly gets coated with insulating dirt and peppered with tiny impacts. You can design around it, but it adds complexity and maintenance pressure continuously. So if solar alone is shaky and radiators are vulnerable, what else can you use to keep the lights on through the long night and handle peak loads? Apollo missions used fuel cells, which combined hydrogen and oxygen to generate a few kilowatts of electric power, while also producing water. That was enough for a small spacecraft with short mission durations. A serious base needs a lot more, tens of kilowatts at minimum, maybe hundreds, to power habitats, labs, rovers, ISRU equipment, and communication systems. Fuel cells can sail up, but they need fuel, and that fuel either comes from Earth, which is expensive, or from lunar resources, which is a whole extra industrial chain. Radioisotope power systems, like RTGs, can give you steady power for years using the heat from radioactive decay, but their output is usually in the hundreds of watts to maybe a few kilowatts, not enough to run a full base by themselves. They're great for backup power, instruments, and small rovers, not for running a whole settlement. That leaves nuclear reactors as the most straightforward way to get reliable, high power day and night independent of sunlight. A small reactor could deliver tens to hundreds of kilowatts around the clock. But reactors are heavy, they need shielding, they raise safety questions, and they come with public relations baggage, especially if they're launched from Earth. So again, the technically strong option is throttled by non-technical issues. Meanwhile, any lander or rover parked on the surface has to deal with cold soak if it sits unused through the lunar night. When temperatures drop toward minus 170 degrees Celsius, around minus 274 degrees Fahrenheit, almost every normal material and fluid behaves badly. Electronics can suffer from thermal stress, solder joints can crack, batteries can lose capacity or get damaged, lubricants can thicken or freeze, structural materials can become brittle. To keep things from breaking, you often need heaters running inside key components, just enough to keep them above some minimum survival temperature. But those heaters draw power constantly, so now you're feeding energy into machines that aren't doing work, just to keep them from dying in the cold. That chips away at your already tight power budget. If you decide not to run heaters and let a rover or lander go fully cold, you then have to prove it can survive being frozen and thawed over and over without failing. That's a major test burden on Earth, plus a risk that the first time it faces a harsher than expected night, it doesn't wake up. Either way, you pay, in power, in mass, in testing, or in reliability. So engineering for the lunar day-night cycle forces you into a narrow corner. You need large, robust power systems that can survive darkness for weeks, radiators that work in vacuum and stay clean enough, hardware that survives extreme cold, and backup systems that cover all the weak spots. None of that is optional if you want people to live there for months or years. And every one of those systems is run by software monitored by sensors and knitted together by control logic. As you stack more power modes, more backups, more autonomous decision-making into the system, the complexity explodes. The next layer of difficulty isn't just hardware anymore, it's the invisible behavior of millions of lines of code that have to work perfectly, in real time, in a place you can't send a repair crew to in a few hours if something goes sideways. Here's the uncomfortable twist. The more advanced your computers get, the easier it is for invisible glitches to kill you, and going back to the moon pushes you straight into that problem. The Apollo guidance computer ran at about 1 MHz with roughly 2 kilobytes of RAM. That's tiny. Your phone does billions of instructions per second with gigabytes of memory. On paper, that sounds like a clean win. More power, more capability, more safety. But Apollo's computer was small enough that engineers could understand most of its behavior. Modern systems are so complex that no single person can hold the whole thing in their head. You're running layers of operating systems, middleware, drivers, control software, redundancy logic, all talking to each other. Every extra layer is another place something can go wrong in a way nobody predicted. So yes, you have more power than Apollo ever dreamed of, but you also have more modes, more interactions, and more ways to fail that are hard to even describe, let alone test. So the obvious question is, if computers are that powerful now, why not just make them smart enough to keep you safe from all the other risks? Why isn't more code always better? Because every new feature you add is also a new surface where bugs can live. Autonomous landing, real-time hazard detection with the cameras and LiDAR, adaptive life support that tunes itself based on sensor input, automated power management for a base, all of that needs software. Not a few hundred lines, but tens or hundreds of thousands of lines of code, sometimes millions across the whole system. You cannot prove that this code behaves correctly in every possible situation. There are too many combinations of sensor values, timing, power states, and hardware glitches. What you can do is test aggressively, simulate a lot of scenarios, use formal methods where possible, and build redundancy so that one fault doesn't immediately kill the crew. But when that code is running in a lander dropping toward the moon at hundreds of meters per second, or in a life support loop keeping oxygen at safe levels, a crash or a lockup is not like your laptop freezing. You don't reboot and shrug, you might not have time to recover. A single pointer error, a race condition between two threads, or a mishandled sensor reading can cascade into a bad burn or a bad decision at the worst moment. The point isn't that engineers are sloppy, it's that the systems are so complex that absolute perfection is impossible, and the stakes are much higher than any normal consumer device. And that's before you add a new threat that Apollo never had to think about: the idea that someone might deliberately interfere with your systems from afar. In deep space, you already worry about cosmic rays flipping bits in memory, so you use error-correcting codes and radiation-tolerant hardware. Now you also have to worry about cybersecurity. As more countries and companies operate in the Earth-Moon region, the cislunar space, your communications links and control paths become targets, or at least potential weak points. You need encryption so that only the right people can talk to your spacecraft. You need strong authentication so no one can inject fake commands. A malicious or spoofed command sequence sent to a lander or habitat is not just an IT incident. If it cycles a valve at the wrong time, points an antenna the wrong way, or initiates an unwanted burn, the end result could be a loss of mission or a loss of crew. Even if nobody is actively attacking you, the possibility means your software and comm stacks must handle more complexity. Crypto libraries, key management, secure boot, all of it has to work correctly in an environment where you cannot send a field technician to swap a router. At the same time, the person on the loop still has to make sense of what all these systems are doing, and that goes through one last critical layer: the human-machine interface. Astronauts don't operate these systems sitting comfortably at a desk with a mouse. They are in cramped cabins, sometimes in bulky suits, with gloves on, possibly tired, dehydrated, or motion sick. They see data on screens, checklists on tablets, LEDs on panels, the way you group information, the colour and sound of alarms, the number of steps in a procedure, all of that matters. Get it wrong and you create confusion right when clarity is critical. During Apollo 11, those 1202 and 1201 alarms popped up during landing because the computer was overloaded with radar data. The alarms were technically correct, but the human interpretation under stress nearly led to an abort because nobody wanted to push through an unknown error in that moment. Modern systems can generate far more alarms and status messages. If you don't design them carefully, you end up with alarm storms, dozens of beeps and warnings triggered by a single underlying fault. The crew then has to decide, quickly, which one is real, which one is a cascade, and what to do next. In a suit with restricted motion, under 1/6 G, maybe at the end of a long EVA, that's not trivial. A bad user interface in a spacecraft or habitat is not just annoying, it can be lethal. So a lot of engineering effort goes into button layout, screen design, procedure flow, and training, and you have to revise it as you learn from simulations and missions. All of this complexity leads to one more harsh fact that people outside the field rarely see: verification eats your schedule and your budget. For every line of code that actually flies, many more lines exist in test harnesses, simulators, logging tools, and analysis scripts. Engineers run hardware in the loop tests where real flight computers talk to simulated sensors and actuators over and over, trying to shake out rare timing bugs. They introduce faults on purpose, cut data lines, flip bits, drop packets to see how the system responds. They review code manually, run static analysis tools, and repeat this cycle many times. From the outside, all you see is a headline saying, "Launch slipped to next year," and it sounds like someone just didn't move fast enough. Inside, a team might have found a 1 in a million bug, a state machine that fails only if a specific sensor spikes while a reboot happens during a power transient. That edge case would probably never show up on Earth. In lunar operations, where you have dust, radiation, temperature swings and no rescue, you have to treat that 1 in a million as completely unacceptable. Fixing it means rewriting code, retesting and reproving that nothing else broke in the process. So at this point, you've stacked physical difficulty, biological limits, hardware extremes and software complexity on top of each other, and that's still not the whole story. Even if you solved every technical problem, you still have to work inside a legal framework that was written when people were barely in orbit, not running industrial operations on another world. The rules about who owns what, who is allowed to do what, and how you avoid conflict on the moon are still fuzzy, and that fuzziness can stall or reshape missions just as effectively as any hardware failure. You've seen how hard the tech is, but there's another layer that quietly blocks progress. Even when the rockets and landers work, the rules about who owns what and who's allowed to do what on the moon are still half-formed. Start with the big rule everyone signed early on. The Outer Space Treaty basically says no nation can claim the moon as its territory. You can't plant a flag and say this patch is the United States or this crater is China in a legal sense. That's good for avoiding old-style colonial land grabs and keeping big powers from carving the moon into pieces. But it's awkward for anyone who wants to spend serious money. If you can't own land, how do you justify building billion-dollar infrastructure on it? A company thinking about mines, fuel depots, or comms hubs asks, what stops someone else from parking right next to us and using our work for free? If governments can't claim territory, they also can't grant clear property titles in the way they do on Earth, so you end up with a tension, peace is protected, but long-term investment feels risky. Then comes the next question investors care about. If you can't own the ground, can you at least own the stuff you dig up? That's where resource rights get messy. Suppose you mine water ice at a polar crater, turn it into drinking water and rocket fuel, or dig regolith and melt it into metal and bricks. Is that yours in a legal sense? Some recent national laws say yes, their companies can own and sell resources they extract in space. Other countries are uncomfortable with that, and argue it violates the spirit of space for all humankind. There's no fully settled global agreement on this yet. You're basically rerunning old arguments from maritime law and deep-sea mining, but now in a place 384,400 kilometers away, where enforcement is hard and everybody is watching for unfair advantage. Until those rules stabilize, big commercial plans for lunar mining or large-scale manufacturing will move slowly because no one wants to pour money into something that can be challenged later as not really yours. Even if you agree on basic ownership, you still have to figure out how not to get in each other's way physically. Say two crews land near the same interesting crater rim or near the same patch of shadowed ice. Who decides how close is too close? Who sets standard safe distances between landers, habitats and power systems? Who manages which radio frequencies are used so that one base doesn't jam another's signals? On Earth, we have air traffic control, driving laws, shipping rules. On the moon, you're starting from near zero. You need agreed-upon safety zones around fragile sites and landing pads, clear procedures for approaching someone else's hardware, and shared norms for things like laser communications or radar use. Without that, one mission's landing plume can spray dust onto another mission's solar panels, or a rover can interfere with someone else's instruments. A minor collision or radio interference up there isn't just a paperwork issue, it can mean damage to life support or a decompression risk. So far, most of this is handled by informal guidelines and bilateral deals, not a single, solid global rulebook. On top of that, a lot of lunar technology is inherently dual use. A communications relay in lunar orbit that helps explorers talk to Earth can also support military operations or surveillance. A radar built to map regolith depth can also track satellites. High-power lasers for communication or power beaming can, in theory, be misused. That means every large piece of infrastructure has a strategic angle. Countries will worry about how neutral installations really are, who controls them in a crisis, and whether someone is quietly using science gear for defense tasks. That blurs the line between peaceful exploration and strategic positioning. Cooperation becomes harder when each side has to assume that the other might flip a civilian system into a military role if tensions rise. So even missions that are marketed as purely scientific or commercial, are evaluated through a security lens, and that slows down agreements. All of this leads to one blunt reality: governance is lagging behind technology. It is genuinely easier to design and build a new lander than it is to create a legal framework that every major spacefaring nation and their companies trust. Engineers can run simulations and tests and eventually say, this design works. Lawyers and diplomats have to balance national interests, commercial interests, security worries, and fairness. And every sentence in a treaty gets picked apart from all sides. So now, space lawyers and policy experts matter as much as propulsion engineers. A single vague phrase about appropriate use or benefit to all humankind can spook investors, or give one country enough doubt to block a joint project. Delays that look like the program is slow are often actually the partners are still arguing over who gets what access, and on what terms. By this point, you've got a full stack of obstacles: physics that punishes you, biology that complains the whole time, hardware and the software that must be near flawless, money that wobble, and a legal framework that's still catching up. So why bother going back at all if everything is this hard? Because the scientific goals that are on the table now are far bigger than plant a flag and bring back some rocks. We barely scratched the moon the first time. The questions on the table now are about the history of the whole solar system, the early universe, and even the structure of the moon's interior. And chasing those answers cranks the difficulty up yet another notch. You might think Apollo finished the moon scientifically, that we went there, grabbed what we needed, and moved on. The reality is, from a science perspective, we barely touched it. Across all 6 Apollo landings, astronauts spent somewhere around 80 hours actually walking on the surface total. That's barely more than 3 days of cumulative time spread over different sites. They brought back about 382 kilograms of rocks and soil, or roughly 842 pounds. That's a lot of rock to look at in a lab, but compared to an entire 3,400 kilometre wide world, it's tiny. Most of the moon has never been sampled directly. Modern science questions aren't just, what is this rock made of? They're, how does this region compare to that region? How deep do the layers go? What's frozen in the polar ice? What's happening meters below the surface? That means drilling, not just scooping, sampling at different depths, and deploying instruments that stay there and watch how the environment changes over years. The bar for good science is way higher now than it was in 1969. So if even those famous moon rocks are only a first taste, what is it the moon is actually storing for you, long-term, in its surface and subsurface? The moon acts like a recorder for the whole solar system. Its regolith, that mixed-up dusty layer, has been built up by billions of years of micrometeorite hits and solar wind exposure. Layer by layer, it captures a history of what's been raining down on it and what the sun has been doing. The ratios of different isotopes in rocks and ices, like different forms of hydrogen, oxygen, or noble gases, encode how active the sun was, how often big asteroid events happened, and how material moved around in the early solar system. To read that record properly, you need clean, controlled sampling. That means drills that can pull out core samples without contaminating them with modern air or water. Storage systems that keep samples frozen or at controlled temperatures, and clean labs back on Earth to analyze them. It also means visiting many different terrains: ancient highlands, younger lava plains, polar regions, deep craters. 1 or 2 landings doesn't cut it. You're talking about a network of missions, each adding a piece to a very long, very detailed timeline. If the ground under your feet holds the history of the solar system, what about the sky above you? What does the moon let you hear that you can't catch from Earth? The far side of the moon is one of the quietest radio places you can get in the inner solar system. Because it never faces Earth, it's shielded from most of our radio noise, the constant buzz from TV, phones, radar, and satellites. That makes it a prime location for low-frequency radio astronomy, especially at wavelengths of tens of meters that are almost impossible to observe from the ground here. Those low frequencies can probe the dark ages of the universe, the time before the first stars lit up when only neutral hydrogen filled space. That's a completely new window on cosmology. But to use that window, you don't just drop one antenna and call it a day. You need arrays spread over kilometers, lightweight antennas or wires laid out across rough terrain connected to central processing units with reliable power and data links. Those arrays have to survive thermal swings, dust and micrometeorites, and then they have to coexist with landers and rovers without picking up interference from your own equipment. Suddenly, your simple science goal turns into a big deployment and operations problem on the far side of another world. If the surface can tell you about the early universe, what can the moon's interior tell you about how rocky worlds like Earth actually form and evolve? To answer that, you need geophysics, not just geology. Apollo did deploy seismometers, heat flow probes and reflectors for laser ranging, and those gave us a first look at moonquakes and interior structure. But the network was sparse and limited in lifetime. A modern effort would aim for a true global spread of instruments, multiple seismometer stations to triangulate quakes and impact events, heat flow probes at different latitudes and depths, and high-precision gravimetry from orbit to map mass distribution. Each seismic station needs long-lived power, robust data links back to an orbiter or relay, and precise emplacement so you know exactly where the readings come from. You might want them in very different terrains, which means multiple landers or rovers to deliver and position them. Then you need to keep them running for years to catch enough events to make good models. This is not drop and forget, it's deploy, monitor, maintain and integrate into a network, in a place where maintenance is extremely hard. All of this sounds amazing, but every new science goal adds another box to the spacecraft, another sensor on the rover, another antenna on the lander. What does that actually do to the mission you're trying to fly? Every instrument has a cost in three currencies: mass, power and data. A drill, a spectrometer, a seismometer, a heat flow probe, a radio antenna. Each one weighs kilograms, draws watts, and produces bits per second that have to be sent back to Earth. As you stack experiments, your lander gets heavier, your power system has to grow, your communication system needs more bandwidth. That forces you to either build a bigger rocket or split the load across multiple launches and multiple spacecraft. The simple picture of one lander, a couple of experiments, one heroic mission breaks down fast. You end up planning a campaign, several landers at different sites, rovers that can move instruments around, orbiters that provide relay links and high-resolution mapping, maybe sample return missions layered on top for the most critical materials. That's a system of systems problem. You have to coordinate trajectories, landing windows, science timelines, and failure modes across many vehicles and many years. Any one failure can break connections the other parts were counting on. So now, going back to the moon isn't just about repeating Apollo with nicer cameras, it's about building a whole scientific infrastructure around and on the moon, capable of answering questions that weren't even on the table in 1969. That's harder, slower and heavier, but scientifically, it's also much more valuable. And here's the key tension. Everything you've heard so far makes the moon sound almost impossible, but we're still pushing for it. Why? Because something else in the background has changed. The way rockets are built, reused and paid for, and the way industry is starting to treat the moon as a place for regular business, not just rare hero missions. If all of this is so hard, is there any real reason to think we can bend the curve? Or are we stuck with Apollo or nothing forever? So after all this, it's fair if you're thinking, okay, this sounds almost impossible, why are we even trying? Here's the twist. In the background, the way we reach space is changing, and that change is the main reason going back to the moon might actually stick this time. First big shift, launch costs are finally moving in the right direction. In the Apollo era, a single Saturn V launch was in the hundreds of millions of dollars. If you adjust for inflation, you're easily talking over $1 billion per shot. Today, with partially reusable rockets, you can get payloads to low Earth orbit for a few $1,000s per kilogram, sometimes less, and that trend is still downward. It is still not cheap. Sending your own body mass to orbit is roughly like buying a high-end sports car, but that's very different from this costs as much as a skyscraper. Every time a booster flies, lands, and then flies again, the fixed costs get spread out, and suddenly things that were insane in the 1970s, like resupplying a station in lunar orbit or delivering multiple cargo landers per year, start to look merely very expensive, not impossible. And this cost drop feeds directly into a second change. Government agencies are no longer the only ones touching the moon. NASA and others are now buying rides for instruments on commercial lunar landers, instead of designing, building and operating every lander in-house. That means small companies can build specialized landers, take NASA or ESA hardware as payload, and try new approaches. Some of those landers will fail. In fact, you should expect a few early crashes. But that's the point. If the price per attempt is lower and the responsibility is spread out, the overall program can survive a couple of losses, learn from them and move on. You start to get something that looks like a lunar logistics market, not a once-per-decade mega mission. Now push that idea one step further. Instead of one-shot landers you throw away after each mission, you're starting to see designs for reusable lunar landers that get refueled either in Earth orbit, in cislunar space, or eventually at the moon itself. Think of it as the difference between one-way ships that get scrapped after each crossing and aircraft that fly a route hundreds of times. A reusable lander might shuttle between a station in lunar orbit and the surface, topping up its tanks from a depot. Once you get that loop working, your marginal cost for each additional cargo or crew rotation drops sharply. That makes the idea of a permanent base and real industry on the surface much less crazy. You're not rebuilding the whole stack for every mission, you're running a service. Around that, you start to fill in the rest of the cislunar neighbourhood. Habitats or gateways in lunar orbit, cargo tugs that push modules between different orbits, relay satellites that give you near continuous communication and navigation coverage. All of that is already being planned. None of this exists just for the moon. The whole architecture doubles as training for Mars and beyond. Operating a small station in lunar orbit teaches you how to manage long-duration life support and radiation exposure outside Earth's main magnetic shield. Running tugs and depots teaches you orbital logistics. Keeping multiple landers and rovers alive on the surface teaches you how to run a distributed system where you can't send a repair team from the next city over. So the difficulty of the moon isn't just bad news, it's deliberate training. You're choosing a target that is close enough to reach in a few days, but harsh enough that you have to solve real deep space problems, not just low Earth orbit ones. The gravity is weaker than Earth's but strong enough to matter. The environment is brutal but reachable. The comms delay is noticeable but not insane. If you can build a semi-routine presence there with refueling, repair and logistics, you have most of the pieces you need for Mars, which is farther, harsher and less forgiving. This loops back to the question that started all of this. Why is it so hard if we already did it? The truth is, the hardness is the point. If going back to the moon were cheap, safe and quick, it wouldn't force humanity to upgrade its engineering, its biology and its economics. What you're really seeing in all these obstacles is a checklist of what a spacefaring civilization has to master. High efficiency, partly reusable launch, robust life support for months, autonomous systems that don't lose their minds, international rules that can handle shared, high-value terrain, and a public that can tolerate long timelines and real risk. Every time a test flight explodes, every time a lander tips over, every time a schedule slips, it's very tempting to say, we did it in the 60s, what's the problem? But that 60s victory was a sprint, a massive short-term push to touch the moon and come home. The thing we're trying to build now is different. It's an actual staircase, a set of steps you can climb again and again, with more people and more hardware each time. That's slower, it's messier. It requires industry, not just heroism. So yes, it's hard, it's supposed to be hard. The real question isn't why is it so hard, it's are we willing to stay focused long enough for the difficulty to reshape us into the kind of species that can handle this, routinely? And that brings up one more obstacle you haven't really faced yet. The hardware can be built, the laws can be written, the rockets can be tested, but none of that matters if human attention and motivation keep flipping from hype to boredom in a few months. The last piece of this puzzle isn't out there in space, it's in your head, in how you and everyone else reacts to danger, delay and repetition, once the first big we're back on the moon moment fades. You keep hearing that the moon is only 384,400 kilometers away, about 239,000 miles, and your brain treats that like just another big number. But in reality, that's roughly 30 Earth diameters away. And if something goes seriously wrong out there, nobody is coming to get you. That distance is a psychological problem as much as a technical one. On Earth, even in remote places, you can picture rescue, a helicopter, a ship, a hospital. In low Earth orbit, like the ISS at about 400 kilometers up, you're still in radio contact with multiple ground sites, and there's at least a path for emergency return within hours if the vehicle is ready. On the way to the Moon, and on the surface, you're several days away at best. If a critical system fails in the wrong way, you can't just launch a quick rescue mission. You either fix it with what you have, or you don't fix it at all. That level of isolation is hard for people to really feel. It looks safer on a screen than it is in reality. Decisions that seem bold or adventurous can actually be playing with a situation where a single cascading failure just ends the crew's story, and there is nothing anyone on Earth can do about it beyond watching telemetry flatline. At the same time, your culture has done something weird with the Moon in your mind. Apollo made it look like a solved problem, and then decades of movies, shows and games turned it into background scenery. The Moon shows up behind spaceships, in concept art, in logos, and you start thinking, we've been there, that's old news. That normalization kills urgency. Voters are wired to chase firsts. The first satellite, the first person in orbit, the first moon landing, the first photo from a new world. Repeats don't trigger the same emotional response, even when the repeat is actually 100 times harder. Because now you're talking about sustainability, logistics and bases, not quick visits. So you get this odd situation where the engineering challenge grew, the risk stayed high, but the sense of, wow, this is new faded. That mismatch makes it much harder to keep money and attention locked on the goal. Now think about the tiny group of people you actually send into this environment, the astronauts. You're not just picking physically strong, smart people, you're selecting for extreme psychological resilience. These are individuals who can tolerate confinement, monotony, long periods away from family, and the constant knowledge that a handful of systems standing between them and vacuum could fail. Training tries to prepare them with analog missions in places like Antarctic stations or underwater habitats, and with long hours in simulators. But those analogs never fully match the combination you get on a deep space mission. The isolation, the time delays, the strange gravity, the constant technical workload. Mental health support becomes a real engineering input. You have to plan for communication time with Earth, including private calls. You need procedures for dealing with stress, conflict between crew members, and the psychological impact of repeated high-risk activities like EVAS in 16G. You need cabin layouts and schedules that avoid pushing people into burnout. All of this uses bandwidth, crew time, and mission planning effort, and it's non-negotiable if you want people to function well over months, not just days. We'll send the toughest people and hope is not a serious plan. Outside the spacecraft, there's another psychological layer, the public watching from the Earth. Public risk appetite and media narratives are brutal to manage. A single fatal accident on a lunar mission will be replayed endlessly, picked apart on talk shows, and used by critics to argue that the whole effort is reckless. Decision makers know this. They weigh not just the engineering risk, but the damage if something goes wrong. The same public that cheers big, inspirational announcements can turn to outrage within 24 hours if a crew dies. Culturally, people want the hero story, the perfect landing, the historic speech, but they don't want to face the statistical reality that serious exploration comes with non-zero fatality risk. That pushes agencies into a tight corner. If they move too slowly and too cautiously, people say their program is bloated and failing. If they move faster and accept higher risk, and something goes wrong, those same voices call it criminally irresponsible. This tension feeds back into every budget decision, every design review, every launch date. It shapes how bold leaders are willing to be, even when the technical team says a certain level of risk is manageable and justified. Then there's the last piece, the story you tell about why the Moon matters at all. From a distance, it's a dead, airless rock. No oceans, no forests, no cities. Convincing billions of people that this place deserves decades of effort and huge amounts of money requires a clear narrative, Are you doing it primarily for science to understand the early solar system and the universe? For survival to learn how to live off Earth before something bad happens here? For resources to mine water and metals and change the economics of spaceflight? For national prestige to show that your country can lead in high technology? If you cannot explain the why in a way that feels coherent and honest, cynicism creeps in. People start to see moon programs as vanity projects, or as covers for military goals, or as distractions from problems on Earth. Attention drifts to the next crisis, or the next shiny topic. Budgets erode quietly, missions get delayed, then descoped, then cancelled. The question why is it so hard slowly morphs into why are we even trying, and once that shift happens, it's very hard to reverse. Behind all of this, there's a simple pattern. Your brain, your media, all pull you towards short-term reactions, excitement, fear, boredom, outrage. The moon demands long-term commitment, stable focus, and a willingness to live with real risk for long-range payoff. That's a mismatch between human psychology and the kind of timeline a lunar infrastructure actually needs. So now you've seen the full stack: physics, engineering, biology, software, law, money, and even attention itself, all dragging against the idea of going back. Which sets up the final question: if everything from gravity to public opinion is fighting you, why do people still argue that returning to the moon and staying there is not just worth it, but necessary? What bigger game are we actually playing when we talk about a sustainable presence on that grey, hostile world? Here's the core of it. Going back to the moon is so hard because the moon is the first place that stress tests your entire civilization at once. Not just your rockets, not just your astronauts, but everything at the same time. Physics, biology, software, law, industry, culture. A short flag-planting mission can hide weak spots. A sustained presence tears the cover off. If you want people living and working 384,400 kilometers away, about 239,000 miles for months at a time, you have to harden every subsystem of how humanity operates all together under pressure. Think about what that actually means. The physics has to be good enough that landings and returns become routine, not miracles. Life support has to run for years, not days. Software has to manage power, navigation, robotics, and communications without melting down in edge cases. International rules have to be clear enough that countries and companies trust they won't be undercut halfway through. The moon is basically asking, can your species coordinate at this level or not yet? It's less like a trip and more like switching humanity into a new operating mode, from planet-locked to multi-site. And here's the frustrating part. There is no single breakthrough coming that suddenly flips that switch. There's no miracle engine that makes the rocket equation harmless. There's no one budget decision that makes risk and complexity disappear. There's no perfect treaty that instantly removes all tension. What you get instead is a lot of small moves. Engines that are a bit more efficient. Launch systems that are a bit cheaper because they're more reusable. Suits that are a bit less fragile in dust. Life support that recycles a bit more water and air. Software that is a bit more robust against weird failures. On their own, each improvement looks boring. It's just a percentage better here, a new checklist there, a slightly cleaner legal definition on some resource rights. None of that feels like the big cinematic breakthrough people expect from science fiction. But these are the moves that actually bend the curve because they stack. 10% less launch cost multiplied by 10% better, mass fraction multiplied by 10% more stability compounds over time, and okay, now we can add another cargo flight per year, now we can keep the base staffed longer, now we can risk more capable missions. The moon gets easier only in the way everything real gets easier, gradually with a lot of unglamorous work. Then you hit the timescale problem. Apollo's main story, from we're doing this to people are walking on the surface, fit inside about a decade. A true cislunar system, depots in space, stations in lunar orbit, bases on the ground, semi-regular cargo and crew traffic, that's going to take multiple decades. The people voting on budgets now, writing regulations now, leading companies now, will be retired or gone when the system really feels mature. You're asking investors, and the public to support a project where the biggest payoffs land in someone else's lifetime. It's hard for markets that live quarter to quarter. It's hard for human egos, which naturally want to see the payoff of their decisions while they're still in the spotlight. So any serious lunar program has to be structured so that each generation gets visible wins along the way. Scientific results, new tech, concrete benefits on Earth, while still building toward a larger architecture they won't fully own. If you don't do that, support decays and the long game stalls out halfway. And where does that leave you? Sitting at home, watching launches on a screen, thinking you're just a spectator. You're not. Public attention is a control input in this system. It shapes what companies think they can sell. When you understand the real constraints, you stop repeating, "We did it in the 60s, what's the problem?" and you start asking different questions. Questions like, how do we share risk between governments and companies so one failure doesn't kill a whole program? How do we write rules for lunar resources that are fair enough to attract serious investment? Those questions sound less dramatic than when's the next moon landing, but they were exactly the questions that make future moon landings possible in the first place. When you bring that mindset into conversations, voting, and culture, you push the system in a direction where long-term projects can breathe. You make it slightly easier for some engineer 10 years from now to argue for keeping a mission alive because the public has learned not to treat space programs like disposable movie sequels. So what's the real answer to why is it so hard to go back to the moon if we already did it? It's hard because we never truly owned that capability in a stable way. Apollo was a planetary-scale stunt, a risky rush demonstration that, under extreme conditions, with extreme funding and extreme urgency, we can do this once. It did not leave behind a reusable staircase. It left behind a memory, some hardware in museums, and a lot of scattered knowledge. Going back now in a serious way means turning that one leap into an actual staircase, something you can climb again and again, with different crews, different countries and different goals. It means rockets that can fly many times, landers that can be refueled, habitats that can be repaired and upgraded, laws and agreements that don't fall apart every time a government changes, culture that can handle failure without quitting. None of that was required for Apollo. All of that is required for a lasting presence. Building that staircase to the moon was never going to be easy, no matter how clear the old footage looks. But if we manage it, even partially, the payoff is bigger than just new flags and new footprints. You shift humanity from being bound to one world, one gravity well, to being something that treats the space around our planet as part of its home territory. And once you do that, the question quietly flips from, why is it so hard to go back to the moon, to, now that we can live there, what else are we finally ready to do? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.